All right, let's talk about something you're feeling right now, but you can't even see it. Gravity. Seriously, getting a grip on the gravitational field is an absolute game changer for your physics exams, whether we're talking WAEC, JAMB, or NECO. So you ready? Let's jump in and crush this topic. I mean, just think about it for a second. What's actually keeping you in your chair right now? Or what keeps the moon doing its thing around the Earth? Or heck, what holds entire galaxies together? Yup, it's all gravity. Today, we're going to pull back the curtain on this invincible force and really figure out what makes it tick. Okay, so here's the game plan. First, we'll get a handle on what this invincible influence is all about. Then, we'll get into the rulebook, the formulas you absolutely need. After that, it's practice time with real past exam questions. And we'll finish it off with a quick recap to make sure you're totally exam ready. All right, section 1, gravity's invincible influence. Before we even think about touching a calculator, we need to get a solid feel for what a gravitational field actually is. You know, why does it matter so much? This is the foundation for everything, so let's get it right. So what is a gravitational field? Here's the most important thing to remember. It's not a thing. You can't touch it. It's more like a zone of influence. Anything that has mass, and I mean anything from a pan on your desk to the planet Earth itself, creates this field around it. And if another object with mass enters that field, it's going to feel a pull. And why does this matter for you? Because trust me, this stuff is all over your exams. It's the why behind planets orbiting the sun, the how for satellites staying up there, and the simple reason stuff falls down. Seriously, if you nail this concept, you're already way ahead of the game for a big chunk of the syllabus. Okay, concept down, now for the fun part. Or maybe the scary part for some of you, the math. This section is all about the universal rulebook. We're going to take these big ideas and turn them into formulas. Think of these as your essential toolkit for solving pretty much any gravity problem they can throw at you. And this is the big one. The master rule, straight from the man himself, Sir Isaac Newton. What's amazing is how simple yet powerful this is. This single sentence describes the pull between literally any two objects in the entire universe. You have got to know this by heart. And boom, there it is in math form. This beautiful little equation is how we actually calculate that force. So let's break it down, piece by piece, so you know exactly what you're looking at. Okay, F is the force, M1 and M2 are your two masses, and R is the distance between them. But look at that big G. That's the universal gravitational constant. And the cool thing about this number, it is the same everywhere. I'm talking everywhere in the universe. Whether you're talking about two marbles or two supermassive black holes, G never changes. That's why it's called universal. Okay, now for little g, the gravitational field intensity. All this tells you is how strong the field is at a specific point in space. And you actually know this one already. Here on Earth, g is just what we call acceleration due to gravity. You know, that 9.8 meters per second squared we're always using, that's it. Next up is gravitational potential. The easiest way to think about this is like stored energy. It's the energy an object has just because of where it is in a gravitational field. Now, you might see that negative sign and get confused. Don't be. It's negative simply because gravity is an attractive force. The field is doing the work for you to pull something in, so we give it a negative value. And that leads us to this cool idea, escape velocity. This is how fast you have to be going to just leave, to completely break free from a planet's gravity and not fall back down. For us on Earth, that speed is a staggering 11.2 kilometers per second. To put that in perspective, that's like going from Lagos to Abuja in less than a minute. Just wow. Okay, listen. Up. Because this is a super common mistake on exams. Mixing up little g and big G. They are not the same thing. Little g is local. It changes. The G on top of a mountain is a tiny bit weaker than the G at sea level. But big G, that's the universal constant, is the same in your classroom as it is in the Andromeda galaxy. Never ever mix them up. Alright, enough theory. We've got the concepts, we've got the formulas. Now it's time for the main event. Let's put this stuff into practice. Because knowing the rules is one thing, but using them under exam pressure is a whole different ballgame. Let's solve some real past questions. First up, a question from WAEC Physics, 2019. Take a look. This one is a classic. It hits you with definitions, a derivation, and that classic G versus G question. Basically, it's a perfect review of everything we've just talked about. So take a moment, read it over. How would you even start this? So for that derivation part, it's actually way simpler than it looks. It's all about connecting two ideas. We have Newton's big formula for gravitational force, right? But we also know that for an object on Earth, that force is just its weight, which is m times g. Since they are the same force, we just set the two equations equal to each other. And look, the mass of the object m is on both sides, so we can just cancel it out. What we're left with is that really clean relationship between g and g. Okay, next up, let's try a JAMB question from 1995. This one's pretty direct. It's all about escape velocity. As soon as you see those words, a specific formula should pop right into your head. Now, the key here is all about energy. The kinetic energy you give an object at launch must be enough to overcome its gravitational potential energy. But here's a pro tip, a really common place to mess up. People forget the factor of 2 in the equation. Just remember this. Escape velocity has that square root of 2 in it. It's actually the square root of 2 times the orbital velocity. Don't forget it. And for our last one, a pretty smart question from NECO. This one isn't about plugging numbers into a crazy formula. It's more of a logic puzzle. It's testing if you really understand the simple connection between weight and the strength of the gravitational field, G. The fastest way to solve this is with ratios. Just remember, weight equals mass times G. Since the mass of the object doesn't change, the weight is directly proportional to G. So, if the G at location X is 2/5 of Earth's G, then the weight at X must also be 2/5 of the weight on Earth. To find the Earth weight, we just do the reverse. We take the weight at X, 480, and multiply it by 5/2. And that gives us our answer, 12 newtons. Simple as that. Awesome work getting through those problems. Seriously, we've covered the core ideas, the formulas, and put it all to the test. So let's wrap this all up. Time for a final, exam-ready recap to make sure you've got the most important stuff locked down. Here they are, all in one place. Your essential toolkit. These 4 formulas are non-negotiable. You have to know them. Write them down, make flashcards, practice with them until you can write them out in your sleep. Make sure they are burnt into your brain before you walk into that exam hall. And finally, some last-minute tips. Remember, if they don't give you a value for G, it's usually okay to use 10 meters per second squared. It just makes the math easier. Always show your steps, especially in derivations. You can pick up a lot of partial marks that way. And please, practice those ratio problems. Once you get the hang of them, you can solve some questions so much faster. So I'll leave you with one last thing to think about. We talked about escape velocity, right? Well, a black hole is so incredibly dense that its escape velocity is faster than the speed of light. Nothing, not even light itself, can escape it. So what does that really mean? It tells us that gravity isn't just a simple pull. It's a force so powerful that it can actually bend and warp the very fabric of space-time. Pretty wild stuff to think about. Alright, that's it for now. Thanks for sticking with me. For more practice questions and solutions, visit examkp.com.